Okay, so I'm assuming I'm okay to start now. Yeah, okay, sure. So yeah, welcome back everyone to the second lecture of this afternoon on ordinary differential equations. So what I would do to start with, I thought I would just recap some of the things that we went over in this morning's lecture, just to refresh your memory. So what we did in the first lecture this morning is we examined first order ODEs, and we looked at several ways that we can solve these analytically and numerically. So in particular, we looked at equations which were separable, and then we looked at inhomogeneous first order ODEs, and we introduced the integrating factor method to solve this equation. And we considered several examples. So we considered the population growth model, which was separable after a transformation. And then we plotted the solution using matplotlib. And then we also examined the RC circuit example, which corresponded to a series circuit containing a resistor and a capacitor, which is driven by a time varying potential. We then solved this using the integrating factor method, and again examined the solution using matplotlib and Python. And then in the latter half of the lecture, I went over some numerical methods. So in particular, we looked at the Euler method and the second order Runge-Kutta. So just to briefly recap, the Euler method is an iterative way of solving the first order linear ODE numerically by starting from a set of initial conditions. Well, first specifying some X interval, and then breaking up this X interval into multiple sub-intervals, which are separated by some step size H. And then what we do is we expand the solution at each of these steps using its Taylor solution, Taylor expansion, and then truncate this at first order. And then what we can do is build an iterative way of attaining the approximate solution to the ODE. And so this is in the form of a recurrence relation. So what you do is you start from some initial X value and some initial Y value. You then plug these into the recurrence relation and then obtain the value of Y at the first sub-interval. And then you feed this back into the equation to then subsequently determine Y2, Y3, etc., up until the specified value of X. And we saw that the local truncation error for the Euler method scales as the square of the step size. So yeah, so or at least it's proportional to the square of the step size. So well, including extra higher order terms. So for small h, we expect the error to go as the square of the step size. We then apply this to an example of a linear first order ODE, or sorry, a nonlinear, in this case, first order ODE, that can be solved analytically. And then, well, we just use the Euler method to numerically solve this equation, and then compare the approximate solution against the exact one. And so this was done using this Python code. So hopefully you got to play around with this in the tutorial session, and have a go at changing step size yourself to see how this affects the quality of the solution that you get from the approach. So yeah, what I showed in the lecture was that generally speaking, by decreasing the step size with this approach, that it tends to give a more accurate representation of the solution. So you can see at relatively large step sizes that the resemblance between the exact solution and the approximate one is fairly vague. And then as we go to decreasing step sizes, it gives a better and better approximation. So one thing you also might notice in the plots is that as you iterate through this recurrence relation, then you generally introduce some kind of error every step. So you can see that at a large X value, so for H is equal to 0.01, you can see that at X values which are closer to the end of the interval, that there is still a slight discrepancy. So this is just an artifact of the fact that we're propagating, as we're solving the ODE using the Euler method, that we're propagating the error through this recurrence relation. So one thing to bear in mind is that when you're applying the Euler method is that if you solve this over or use the method to obtain y over a large x range, then your solution will get increasingly worse at large x values, just due to the fact that this error gets propagated and then compounds for larger values of x. Okay, and then what we introduced was the so-called Runge-Kutta method. So this is another type of a numerical approach to solving linear ODEs, and it's based on a kind of similar idea of setting up a recurrence relation to obtain the value of the solution y at some x value xk plus 1, and you obtain this from its previous value at xk. And so the idea with the Runge-Kutta method is that it implements a slightly more sophisticated approach where we don't assume that the derivative of f is constant over each subintervals. We approximate it by taking the average of this over the interval x to xk to xk plus 1. And the consequence of this is the fact that the error now scales as the cube of the step size rather than the square of the step size. So in that regard, we can expect the Runge-Kutta approach at second order to converge much more faster to the exact solution with decreasing step size. And so, yeah, I just gave you the recurrence relations for this. Also just to point out that some of you helpfully noticed that in the tutorials that I've made a couple of typos on this slide. So I've just updated these typos. So I think in the original set of slides, this yk value was xk, and also each of these yk values was also an xk. So the lecture slides on the after this lecture, I'll update the lecture slides to rectify these typos. So yeah, this gives you the iterative procedure that you apply with the second order Runge-Kutta, and then you can also develop schemes that go to higher order. So so for example, at fourth order in the step size, then you implement this iterative procedure to find the value of y at xk plus 1. And you can build even higher order schemes for doing this. So the idea is that at higher order, you tend to produce a more accurate approximation of the solution. But the cost of this is the fact that you generally have to store more values at each step in the procedure. So this can generally increase the computational cost of solving the problem. Okay, so then we looked at the same example. So the example where we can obtain an analytical solution, and then we implemented the same Python code, except we just changed the recurrence relation that we use to obtain y at xk plus 1. Okay, and then as we found that in this example, and hopefully what you also found with some of the tutorials, was that with the second order Runge-Kutta is that it generally gives you a better approximation of the exact solution with decreasing step size. So it basically converges faster. So in this case, you can see that at much smaller step sizes, so at h is equal to 0.01, that this gives an almost exact approximation of the exact solution. So again, just to clarify here, this blue line is the exact analytical solution, and the orange one is the approximated one using the second order Runge-Kutta. Okay, so I think that's where we finished in this morning's lecture. So in this lecture, what I'm hoping to do is to at least cover partly how we can solve certain types of higher order linear differential equations. So in particular, focusing on homogeneous second order linear differential equations, and then I'll apply this to an example in physics, and then we'll again use Python to examine the solutions that we obtain for this example, similar to what I did in this morning's lecture with some examples of linear first order ODEs. Okay, so if we now go back to almost the first slide that I had in the first lecture, so the general definition of a linear nth order ODE is that it's a family of equations for some unknown function y, which can be written in this form. So where in this expression, an and all the way up to a1 and a0 and b of x are just arbitrary differential functions. And we discussed the fact that if we want to solve an nth order ODE, or we want to attain a unique solution to an nth order ODE, then the solution will in general depend on n unknown constants. And so we need generally n boundary conditions or initial conditions to then to obtain a unique solution. So what we'll do in the remainder of this lecture is focus on the homogeneous case, so where this this b of x is equal to 0, and then we'll look at the ways in which we can solve equations of this type at second order. So so in this panel, I just showed the definition of the homogeneous version of this nth order linear ODE, and what we can note is that if we want to solve this, that the general solution to this ODE is going to have this general form, so it can be expanded as a linear combination of each of these functions y1, y2, all the way up to yn, where we assume that each of these y1, y2, all the way up to yn, each individually satisfy this homogeneous nth order ODE. And you can, well, if you assume that, you can verify yourself that if you just substitute this solution into y, then if we assume that each of these y1, y2 individually satisfy this equation, then the linear combination of them will also satisfy this equation. And so the crucial point here is that when we write down the solution, we assume that each of these y1, y2, etc., are each linearly independent. So I won't go into detail what I mean by linear independence, but generally speaking, a set of functions are said to be linearly independent if their sum multiplied by a set of constants is equal to 0 for all x. Or in other words, basically, that each of these individual functions can't be expressed in terms of any of the other sets of functions. So in this case, y1 can't be expressed in terms of any other linear combination of y2, y3, etc., etc. Okay, so what we will do is look at the case in which we have a linear nth order ODE with constant coefficients. So the method for then solving this is that we try some ansatz, which we can generally write in this form. So it's just equal to some fixed constant a multiplied by e to the lambda x. And so the motivation for trying this ansatz solution is the fact that we know that that if we take the derivative of e to some e to the lambda x, then this is just going to give us the original function back multiplied by lambda to the power of whatever our derivative is. And so we can then see if we substitute this into the above equation, then we can just divide through, or each of these terms is going to contain a factor of e to the lambda x. So then we can divide through by both sides to remove the dependence on e to the lambda x. And then this will just generate the following equation, which is called the auxiliary equation. So this is just an nth order polynomial in these coefficients lambda. And so as you might already know, any nth order polynomial in general has n solutions or n roots. So what that means is that we can factorize this polynomial into lambda 1 minus lambda n multiplied by lambda minus lambda n minus 1, etc., all the way up to lambda 0 and lambda 1, sorry. Okay, and so each of these, what we'll then obtain is a solution which can be written as a linear combination of terms of this type, where lambda is substituted each for lambda 1, lambda 2, etc. So in the case where each of these lambdas are real, then we can note the fact that e to the lambda 1x, e to the lambda 2x, e to the lambda 3x, etc. are all going to be linearly independent. So I'm not going to prove this, but you can just take my word for it that each of these terms will be linearly independent. And so what we can then do is construct the solution that I showed on the previous slide in terms of just these exponential functions. Yeah, so if I just quickly go back to the previous slide. So when I stated here that you can in general write the solution to the homogeneous equation in this form, that's what we've done here, just using the fact that each of these e to the lambda x, e to the lambda ix are linearly independent when all these lambda I are real. In the case where you have some mixture of real lambda and complex ones, then we can note the fact that some of these complex lambda i's will always occur in complex conjugate pairs. So in the case where, for example, lambda 1 is complex, then we can guarantee that there's going to be a lambda 2, which is just the complex conjugate of this. And so in general, this our solution, if we just consider the simple case where there's only two these constants, lambda 1 and lambda 2, then the solution would be formed, the solution to this, in this case, second order ODE would have this form, which we can then in general write in the following way. So here, alpha and beta are the real and imaginary parts of, in this case, lambda 1 and lambda 2. In the case where some of these lambda are degenerate, so that's in cases where some of the lambdas are equal to each other, then the solution that we have to obtain is slightly more complicated. So I'll go into this a bit later later on in the lecture. Yeah, so just to clarify, if two of these lambdas are degenerate, it just means that they're equal to each other. So the reason why this is slightly more complicated is that if these are equal to each other, then just writing down the linear combination of these in the form of e to the lambda 1x, e to the lambda 2x will no longer, each of these terms will no longer be linearly independent. So we need to come up with a slightly more sophisticated way of solving the equation. Okay. So the example that I was interested in examining was the damped harmonic oscillator. So this is, for those of you who have study physics, this is kind of like one of the canonical examples that you examine when you look at solving second order linear ODEs. So what this describes is essentially the physical situation where we have some kind of mass which is attached to a spring, and then this mass just oscillates back and forth based on the action of the spring. And this type of system, at least in classical physics, can be described by Newton's second laws of motion. And so when you apply Newton's second law of motion in this situation, you essentially end up with the following second order ODE. And so here, what x is just a function that describes the displacement of this mass from its equilibrium position. And this gamma and omega naught coefficients, what they describe. So gamma essentially corresponds to or sets the damping rate of this mass as it oscillates. So what the second term in this equation describes is essentially the effects of friction on the oscillator. So we assume that this friction is proportional to the speed at which the mass is moving. And then this third term depends on this coefficient omega naught, and this sets what's called a natural frequency of the oscillator. So this is just the frequency at which this mass oscillates on the spring in the case where the damping or this gamma constant is just 0. Okay, so we want to solve this equation now in the case where we have these initial conditions. So if you recall from the first lecture, I said that in general, an nth order ODE requires n boundary conditions in order to find a unique solution. So in this case, because we're dealing with a second order linear ODE, then we need two initial conditions. So one relating to the position of the oscillator at the initial time, and one relating to the speed of the oscillator initial time. Okay, so the starting point is we just use this ansatz that we introduced on the previous slide. So we start by assuming that the solution can in general be written in this form. And then we use this to obtain the so-called auxiliary equation, which in this case will be a second order polynomial since we're dealing with a second order linear ODE. So in this case, hopefully you should be able to show that the auxiliary equation is in this form, and this is quadratic, so we can solve it using the standard quadratic formula. And what you find is that that we can obtain two eigenvalues, which are in fact complex conjugate pairs of each other. So so here what I've done is introduced a new parameter, which I call omega, or capital Omega. And this is just equal to the square root of the square of omega naught minus the square of the damping rate. Okay, and so in this case, because if we assume that generally speaking that omega naught and gamma are not equal to each other, then we can see that each of these lambdas are generally different, so they're non-degenerate. So then we can then form the solution just as a linear combination of these two exponentials with these coefficients C1 and C2. So yeah, so what we can do is we can, as I mentioned on the previous slide, we can, because these, the roots of the auxiliary equation are complex conjugate pairs of each other, we can in fact write the solution in a slightly more convenient form. So what we do is we just simply apply like Euler's formula. So as you might know, that e to the ix is equal to cos of x plus I sine of x. And so we can just apply this. Well, firstly, we can factorize out e to the minus gamma t, and then we just apply Euler's formula to each of these terms, and then we can rewrite the solution in this form, where we can then introduce two new constants which depend on C1 and C2. So here I just call these D1 and D2. So this solution is slightly more convenient just to later examine the behavior of the solution. Okay, so we've established now that in the case where we assume that these lambda 1 and lambda 2 are non-degenerate, then the solution can be written in this form. And so, as we do in all, whenever we want to solve any type of ODE, we then proceed to determine these unknown constants D1 and D2 from the initial condition. So we start by just simply substituting, or just setting t is equal to 0 in this expression. On the left-hand side, we'll just have x0. This first term will just be 0. The second term will vanish. And e to the minus 0 is just 1. So then just trivially, we see that this first unknown constant is just equal to the initial position of the oscillator. So then to find out what the second unknown constant is, so d2, we can take the derivative of this general solution. So again, I haven't shown the form here explicitly, but this can you can do this yourself. And then what we do is set t is equal to 0, and what we obtain is this expression. So here v0 is the initial speed of the oscillator, and then we can obtain d2 in terms of the initial speed, this damping rate gamma, the initial position, and also this coefficient omega. Okay, so if just putting this all together, we've then established, according to these initial conditions, that the general solution to this problem can be written in this form. So we can immediately see that by just looking at this, we can infer three different regimes of behavior based on the value of these coefficients, omega, omega naught, and gamma. So in the case where, so if you recall that large omega, which is equal to the square root of omega naught squared minus gamma squared. So in the regime where omega naught is greater than gamma, then capital omega will just be real. And so therefore we can see that what will happen is that oscillator will just start at some initial position and then undergo damped oscillations until it eventually reaches equilibrium. So these oscillations occur due to the fact that we have these cos and sine terms. And so these oscillations will have a periodicity of well, 2 pi over omega. And so, yeah, another regime would be the case where omega naught is less than gamma. Or should I say, I should say that this first regime is usually called the underdamped regime. So the in the other case where omega naught is less than gamma, then we have to take into account the fact that this this capital omega is no longer real. But what we can do is we can take out a factor of -1. So in the expression, the square root of omega naught squared minus gamma squared, we can just take out a factor of square root of -1, which is just I. And then we can introduce a new real coefficient, which I call here omega tilde. If you then put this back in this expression, you then find that that you basically, each of these cos and sine terms are transformed into hyperbolic functions, cosh and sinh. And so cosh and sinh generally can be written in terms of just exponential, so they don't contain any, they're not periodic functions. So then what happens is that our oscillator in this regime just undergoes incoherent damping, essentially. And so the final regime of interest is where we have what's called critical damping. So this is the case where omega naught is exactly equal to gamma. And as I said, this corresponds to the case where each of the two solutions to the auxiliary equation are degenerate. So this is a kind of special example that relies on us having to choose a slightly different ansatz to solve the equation. So initially what we'll do is just examine the behavior of the oscillator in the underdamped and the overdamped regime, and then we'll go back and look at how we can solve the ODE in the case where we have this kind of critical damping. Okay, so as I did in the first lecture, what we can do is just take this analytical solution and then plot it in Python just to give a feel of how our system behaves with different values of these parameters, gamma, omega naught, and large omega. So on the left-hand side of this panel, I just included a snippet of code that allows you to just plot this solution to the second order ODEs just for varying values of this damping constant gamma. And so what we do is we just start by defining a numpy array, which just contains all the values of t that we want to plot the solution for. And so I also then introduce a list of values of this damping coefficient gamma that I want to plot. And then just for this example, I've just chosen the frequency on units of 2 pi, the frequency of the natural frequency of the oscillator to be 2, its initial position to be 1, and its initial velocity to be 0. And so to plot this, what I also do is define the solution here, x, in Python as a lambda function, which in general depends on this gamma, this capital omega, and this time parameter t, So inside these brackets here, I've just included the solution that I provided on the previous slide. So then what we can do is then just introduce a for loop, which for each of the values of gamma contained in this list, I just plot the solution. What you should also be aware of the fact is that for this case, we have to be careful when we consider values of gamma in which omega naught becomes pure imaginary. So this is just due to the fact that in Python, if you do np dot square root of a negative number, it will generally return a nan value. So to avoid this, what I do in this for loop is just check the condition of whether omega naught is greater than or less than gamma. So in the case where omega naught is greater than gamma, so this is the underdamped regime, then we can just define omega naught in this way. In the case where this is pure imaginary, then we have to manually add this I constant, just due to the, as I said, if you try to do this without, if you try to do this with the argument to np dot square root being negative, then it just won't work. It'll just return a nan value. Okay, so then in this line, we just plot the solution for each of these different values of gamma across this time interval. And so what we see on the right-hand side is just the plot that's produced by this snippet of code. And what we see is that in the underdamped regime, so here we have two lines which correspond to the, or sorry, three lines which correspond to the underdamped regime. So this is the blue, the orange, and the green line, and then one line where gamma is greater than omega naught, which corresponds to the underdamped regime. So as I alluded to on the previous slide, in the underdamped regime, you have these sinusoidal oscillations which become exponentially damped within increasing time. So this is kind of intuitively what we expect in this situation. If we start, if our oscillator is attached to, or if our mass is attached to a spring, that's at some fixed amplitude, and then we let it go, what will happen is it will just oscillate until eventually settle at some equilibrium value, which here is just by definition, x is equal to 0. And so as we increase this damping constant, we can see that the amplitude of these oscillations just decreases, and also the position value decreases faster until we eventually, when we increase gamma enough, we then enter the underdamped regime. And in this case, you can see that the sinusoidal oscillations just completely disappear from the solution. And what happens is that the amplitude just decays and then just eventually settles on its equilibrium value. Okay, so this is in the case where I've chosen the initial position of the oscillator to be away from its equilibrium value, and also the initial speed to be 0. So what you can do is play around with this code and just choose initial conditions to see how this affects the behavior of the solution. So just on this slide, what I've done is just change this such that the oscillator now starts at its equilibrium position, but started it or initialized it with a non-zero speed. So and then this code is exactly the same. I've just changed the values of x naught and v naught, and then you can see that on the right hand side we get this new well, the plots are slightly different, but you still exhibit this similar type of behavior where in the underdamped regime we have these sinusoidal oscillations, and then as we enter the underdamped regime corresponding to this red line, then these oscillations disappear, and we just have this, well, it rises to a fixed point, and then we just have exponential decay to its equilibrium value. Okay, so this demonstrates how we can solve a second order linear ODE in the case where the roots of the auxiliary equation are non-degenerate. So what we can also do now is consider the slightly more complicated example where we have degeneracy in the solution. So if we just go back to the slides I gave maybe 4 or 5 slides ago, where I talked about how you can solve an nth order ODE with constant coefficients. So what we do is we just revisit this. Again, if we try this ansatz, we note that we'll obtain the same auxiliary equation, which again has n roots. So in the case where the solutions to this auxiliary equation contain k degenerate values, so this is what I mean here by k-fold degeneracy. So where, for example, lambda 1, lambda 2, up to some value k, which is less than n, are the same, then we have to then modify our ansatz to reflect this degeneracy. So the reason that we have to do this is because, as I said, each of the terms that we construct the solution from have to be linearly independent. And if we didn't do this, then that basically wouldn't, the terms that we use to construct the solution wouldn't be linearly independent. And so one way we can modify this to ensure linear independency is for each of these lambda values which are degenerate, what we do is we use a solution of this form. So this is just of a similar form to that I showed in the case we have non-degenerate values, but now what we do is we multiply each of these constants by a power of x. So for C1, we just have this constant, and then it goes in increasing powers all the way up to x to the power of k minus 1. And again, I won't go into detail about this, but what you can in fact show is that each of these terms contained within this brackets multiplied by this exponential are indeed linearly independent. And then for the remaining, so this assumes that we have some roots of this equation which are degenerate, and then some other ones which aren't degenerate. So the ones which aren't degenerate, we just treat them in the same way as before, where we just again add these onto the solution. Okay, so this just establishes how we can solve an nth order linear ODE in cases where we have degenerate roots to the auxiliary equation. So just in the kind of the simple example where we're dealing with a second order linear ODE, then we only have 2 roots to this auxiliary equation. And so in the only case where we'll encounter degenerate values is in the case where lambda 1 is equal to lambda 2. And so here the solution to this ODE can in general be written in this form. And then obviously these coefficients C1 and C2 then have to be determined based on the initial conditions that we specify for our problem. Okay, so with this in mind, we can then just revisit the example that I gave before, and then obtain the solution in the case where we have this kind of so-called critical damping, which is when the natural frequency of our harmonic oscillator is equal to the damping rate. So in this case, when we apply, as I mentioned, that in this case the 2 roots of the auxiliary equation are degenerate, so they're the same, and that's just due to the fact that the second term is 0. And so what we can then do is to solve the ODE in this case is we then adopt this modified solution, which so yeah, this is just the same as the solution I gave in the previous slide. And then again, we have to just determine each of these C1 and C2 coefficients based on the boundary conditions that are specified. So here I just choose the same boundary conditions which are given in terms of the initial position of the oscillator and its initial speed. And so now just using the solution, we start by substituting t is equal to 0, and it's pretty easy to verify that that the C1 term or C1 constant is just equal to the initial position of the oscillator. To then obtain the second coefficient, we take the first derivative of the solution. And then this allows us to apply the second boundary condition, which depends on the first derivative of x applied at t is equal to 0. So in doing this, we get this equation. So this just tells us the velocity of the oscillator, or the speed of the oscillator, sorry. We then substitute t is equal to 0, and then based on this expression, you can then verify that we obtain the following, and then trivially, this then allows us to determine C2 in terms of the damping rate gamma, the initial position, and also the initial speed. So when we put all this together, what we end up with is a solution which is of this form in the case of critical damping. So as you can see, this looks quite different to the case that I showed before, where we had non-degenerate roots to the auxiliary equation. So in particular, previously we had the solution depended on, well, it also depended on e to the minus x, but it also depended on these sine and cos terms. So now obviously this solution doesn't contain these sine and cos terms, and just has a kind of also a linear dependence on time. Okay, so what we can then do is just kind of play the same game as before, where we can just examine how this solution varies with different values of these constants, gamma and omega naught, and also specifying different values for the initial position and the initial speed. So in the case where we assume the initial speed to be 0, and the oscillator is positioned away from its equilibrium position, then what we produce is the following. So again, this code is essentially the same that I showed on the previous slide, but just modifying it to take into account the fact that the solution is a different form. But essentially, it's just doing the same thing. So it's just defining our solution x in terms of a lambda function, and then just iterates. So within this for loop, it then just iterates through these different values of gamma that we want to plot the solution for, and just plots the solution for each of these values. And so on the right hand side, you can see that for small values of gamma, we have this very slow decay, so monotonic decay to equilibrium. And then as we increase the value of the damping rate, then this increases the rate at which the solution reaches its equilibrium value. So interestingly, here you can see that the behavior is completely monotonic. So there are no, as we would expect, there's no oscillations in the solution, which we had in the case of underdamping. Okay, so again, we can just modify the initial condition slightly to see what happens in the case where we start from our equilibrium position but have a non-zero speed. So again, we see this kind of like non-oscillatory behavior, but now what happens is that we do have non-monotonic behavior. So what happens is that the amplitude of our oscillator just increases up to some fixed value, which increases with a decreasing damping rate, and then eventually just decays slowly to its equilibrium value. Okay, so I think we have, how much time do we have left? I think just under 10 minutes. So I'm not sure if I'll have enough time to go over completely the case in which we're dealing with a or inhomogeneous nth order ODE, but maybe I can just briefly go over how we can, or just at least introduce you to the idea of how we can treat nth order linear ODEs in the case where we have an inhomogeneous term. So yeah, I won't perhaps get to finish this, but let me just discuss this. So okay, if we go back to get into then just look at the definition of an nth order linear ODE. So in its general definition, we have a dependence on this extra function b of x. So in the homogeneous case, we assume that this was 0, and so all the methods that I just been over apply to the case in which this is true. So the inhomogeneous case is naturally harder to solve than the homogeneous case. But what we can do is note that the approach to solving inhomogeneous nth order linear ODEs is to assume the solution now has this particular form. So this is written in terms of what's called the complementary part of the solution and the particular integral. So let me just explain slightly what these are. So so what this complementary part of the solution is just the solution that you obtain to the homogeneous version of the nth order linear ODE. So that's the case where b of x is equal to 0. So in the general case, that can be solved just using the approach that I just went over on the previous slides. But now what happens is that our solution has also an extra dependence on this new term, which is usually referred to as the particular integral. And so the reason that we can construct the solution in this way is because of the fact that these equations are linear. And so, yeah, let me just go over. So the general method for solving an nth order linear ODE with an inhomogeneous term is to first start by solving the equation in the case where we assume b of x to be 0. And so again, this is just follows what I showed on the previous slides. So we introduce an ansatz, we then obtain the auxiliary equation, and then we solve the auxiliary equation to obtain n values of lambda, and then obviously our solution will have a particular form depending on whether each of these lambdas are real, or whether we have complex conjugate pairs, or whether we have some kind of degeneracy. Unfortunately, in the case where we have an inhomogeneous term, there's no real general method for determining what the second contribution to the solution is, so what this particular integral is. But there's different kind of trial forms of this function that you can adopt depending on what the function here b of x is. Okay, so maybe I'll just finish this lecture now, just giving you some examples of what you can assume the particular integral is for different values of this, or different forms of this inhomogeneous term. So in the case where our inhomogeneous term is written as an exponential, which depends on this constant r, then we can select this. We can set the particular integral to also be of the form of to be of a similar form of this term, multiplied by some constant. So I should maybe have used a different notation here. So just to specify that this b is not the same as this function here. This is just some unknown constant. So in the case where this can be written as a linear combination of sine and cos terms, where potentially either one of a1 or a2 can be 0, then what we can do is we can again assume that the particular integral has a similar form to this, to the function b of x, and then write the particular integral in this way. And then finally, in the case where our inhomogeneous term is written as a sum of increasing powers of x, then again we can assume that the particular integral has a similar form but with different coefficients, b0, b1, etc. And so then the general idea is that we then have to, well, as I said, what we do is to first solve the equation in the case assuming that our inhomogeneous term is 0. So this just gives us the complementary part of the solution. And then what we do is we then solve for the particular integral based on whatever our function b of x is. So in each of these three cases, we try different kind of trial ansatz for our particular interval. And so what we then do, as before, is to find out what these coefficients are based on the particular problem, is that we're going to have to determine these from the initial conditions. So what you do is you then have to substitute the particular interval back into the ODE, and then using the boundary conditions, you should then be able to solve for each of these constants. Okay, I don't think I have enough time to really go over much more, since it's almost 3 o'clock. So yeah, I think that, so at 3 we start with the second tutorial, I think.